So I think that I have to share the screen on this thing. So is it already recorded? We'll start recording if we go. Yeah. It's recording or not. So it's 9 o'clock. So we'll start. We'll start off with Ryan's going to present to us a paper that goes. Isabel said last week we had a presentation that was more kind of a general overview of heat transfer, fluid flow, and particularly powder bed fusion. Ryan's going to talk a little bit more in depth of that survey paper did here. This paper is specifically about the specific problem. Let's do a little more in depth, but within something.
Appreciate it. So, good morning, everyone. Dr. Halsey mentioned this paper titled Heat Transfer and Fluid Flow in Additive Manufacturing by A. Radhaven et al. So a quick introduction, just to give a little bit of background. Some of us may know a big challenge in additive manufacturing parts and quality control is in the microstructure of the parts and repeatability and understanding what the characteristics of that part end up being at the end. So what this paper kind of goes into is a study of effects from a laser-based additive manufacturing process control technique using surface melt pool geometry to kind of real-time monitor the production of the part, provide feedback to the system to kind of ensure quality. And then this analysis was completed using a laser welding model, which was assumed to represent this process pretty closely. A couple of things I want to discuss. One is the melt pool depth inconsistency, changes in laser power level and effect on the melt pool, the solidification characteristics with varying power throughout the build, and then a couple of conclusions and recommendations. So before I get into some of the more interesting stuff, I wanted to quickly discuss the mathematical model and some of the physics that went into this laser welding model. It's based on conservation equations. As you can see from the right, the conservation of mass, not too complicated, just the rho v term, differential goes to 0. The momentum term is that same mass flow term plus the rho v squared, which is mass v squared. Should look pretty familiar. Then the energy equation is a bit longer, but it adds in heat and keeps in a couple of these other terms. The model was declared to be validated in the study, and it was used to solve for fluid velocities and enthalpies in the system. One more calculation I thought was kind of interesting, the laser power density. So basically, this equation calculates the density of the power coming from the laser at the surface of this part. A quick discussion on what these terms are. The Q is the laser power, the F is the power distribution factor, the eta is the laser energy absorptivity, R sub B is the laser beam radius, and the X and Y are the location coordinates. So you can see kind of intuitively this makes sense. As the laser power goes up, your density goes up as well, but as the laser beam radius goes down, that density goes up as well. So one thing I thought was interesting, the absorptivity in this density is pretty dependent on the powder characteristics. As as your powder varies, for example, like the particle size density, distribution, feed rate, things like that, this absorptivity is kind of a variable. So they did mention this in the paper that this is kind of an assumed value, but this can change based on your actual system. So first topic, the melt pool depth. So the theory of this process control, as I kind of mentioned earlier, is that if we kind of control the melt pool shape as the part is created, we may be able to kind of know what the characteristics look like on the other side, or control them to be consistent throughout the part as it's being built up. And in this particular example, 2 lasers of varying power and V radius are used to create these very similar pool geometries. So you can see in the figure on the right here, hopefully you can see that okay. The actual shape of the 2 pools is very similar. It's about 1 millimeter in length and about 0.5 millimeter across. This is just half of that pool, so it's about a 1 by 1 millimeter circle. One thing of notice is this bottom portion of the plot here is the depth. So for the left example, 450 watt laser with a 0.2 millimeter beam radius, you can see the depth of the pool is much larger than the 460 watt laser with the larger beam radius. So as you can see, even though the surface geometries are similar, the depth throughout this pool is not consistent. Quick note of the cause of this. So, as I mentioned, the laser beam radius, the smaller value, had the deeper melt pool depth. This is due to a concentration of the energy, which causes an increased peak temperature. And you can see in these plots on the right here, I'll kind of talk through them real quickly. The top plot is the smaller beam radius, so the higher density. You can see the surface temperature, this solid line, gets up to all the way north of would be about 2,900. And then the dashed lines are subsurface temperatures at 1 millimeter and 2 millimeters. But you can see even these subsurface temperature, these subsurface locations are getting above that liquidus point. The bottom plot is the larger radius, so the lower power density. You can see a much lower peak temperature, and some of the subsurface levels are kind of staying below that liquidus temperature. So one thing that this affects is the cooling rate. So you can see you have kind of a sharp decrease from that cooling rate, and this can also affect the microstructure and eventually the quality of our part and the material characteristics. Let's see. Next topic we want to discuss is the build temperature variation. So one thing we've kind of talked through recently in this class is as you're building a part, as that part gets larger and you're getting close to completion, the temperature of the part actually increases. This is due to exposure time to the heat source, the laser, and as the part gets larger, it's able to hold in more heat. So one thing this study investigated was if my part starts with a temperature, in this case 500 degrees, we lower our laser power to create the same geometry of melt pool. In this case it was 300 watts. So once they have the same geometry of melt pool, at 450 watts, no build temperature, and 300 watts with 500 Celsius build temperature, what does this do to our quality of our part? So as you can see on the plots here similar to before, the left is the original plot we discussed, the 450 watts with the 0.2 millimeter beam radius. And on the right is the new one at 300 watts with an increased initial temperature of 500 degrees Celsius. So again, the geometries are very similar, about the same shape and size. And even more so now, the depth is much more consistent. And even to the point where the temperature gradient across the pool looks a lot better than it did before. So seemingly this would be much better than the previous case, but we'll look into if that's actually true. So the effects of power reduction, as the part temperature increases, there's less energy needed to melt the power, less energy input to get to that melting point, so the lower laser power needed. This intuitively makes sense. What this does, though, is as the difference between the part and the melt pool decreases, your temperature gradient decreases. And your temperature gradient is, as this equation here, third bullet point shows, a large part of your cooling rate. So you can see these plots here on the left, as your heat input goes down, your ratio from T peak to T boiling is kind of a linear decrease, which is affecting that gradient. And then this is actually a plot of just the cooling rate, and as your part temperature increases, again, your surface and subsurface cooling rates are just linearly declining as we go. So again, as these differences in cooling rates pop up, we get a variance in material properties, which affects the quality and kind of breaks outside of our process control. So again, these two examples here are the 450 watt example with no initial heat and 300 watt with 500 degrees of heat. And you can kind of see here one thing that creates big difference is this cooling rate, especially at these peaks here. And then on the right-hand side, once you get below liquidus and this metal is kind of solidifying, the first example, kind of a sharp decrease down to about 2 seconds in this plot. The second example, with the higher temperature and smaller gradient, kind of drags and slides out a little bit. One thing this also affects is the time above this beta transit. So I know for titanium, this is titanium 6-4 example, the outputs of beta transformation is kind of key in the quality of the metal, characteristics of the metal. I don't have a huge materials background to know exactly what that transformation means to us, so I wanted to kind of open up to class and Dr. Helsley and see if there's any more insight into that. So I don't know, what are your thoughts? understand that.
Basically, equilibrium states, if you hold it at a certain temperature for a long time, it creates a certain microstructure. And because you can freeze in certain transient phases, but I'm not going to say certain, basically, if you cool it really fast, you can freeze in a certain microstructure. But if you were to hold it for that period of time, it's actually going to freeze a shape, and you're not going to have a microstructure. So the time at which you hold a material in a certain temperature is important. And when you're going through the different phases in a phase one. So I assume this is what they're getting at here. In terms of this very sharp gradient, they can freeze in the phase that they want. And if they were to hold it too long, it should under the phase go away.
Okay. Yes, because there's a lot of emphasis on the gradient itself and how that impacts your microstructure. And obviously, as that changes, the quality of your part is going to change throughout. It's going to be hard to predict how that part will react to stress, and things like that. And they also mentioned this alpha beta transformation occurrence and how that kind of plays in. So probably similar, but just wanted to kind of mention that.
Are these like alpha and beta transformations different from like austenite, the bases that you talk about? Is it part of the phase diagram of the metal or?
No, I think it's something unique to titanium. I think it's something in the structure itself that as you heat it above a certain temperature, it starts to change the makeup of that kind of property, and it kind of transforms over to beta, and I think it can come back once you're above that temperature. So the longer you're up there, the more of that happens. Like I said, I don't have a huge materials background, and I'm not overly familiar with what that does for us or what that really means.
You can take what you want out of this plot, but it's essentially showing different temperatures. So this would be depending on the concentration of basically is alpha and beta temperatures.
Okay, we'll move on. Some quick conclusions and recommendation. So this study kind of showed, and the overall point of this study was that there are a few problems with this idea of just implementing process control based on the surface pool geometry. Mainly it's in the material properties and how they're affected by more than just that surface pool geometry. Obviously the 3D shapes and the depth can play a big role. The thermal cycles, how that temperature, how quickly it comes back down to that solid state. And then again, there's cooler radiuses, how quickly we can freeze those microstructures. The recommendation moving forward was to add fidelity to this process control implementation. The use of numerical methods should be employed to predict the items summarized above. So instead of just looking at the shape, look at the temperatures and how that affects the depth, the concentration of power, gradients, kind of things like that on the fly to feed that back to the system as opposed to just the visual scheme. So that's all I have.
Do you have any specific recommendations on how to modulate laser power as you go higher in the part, the background temperature gets higher?
So they had some discussion, not necessarily on how you would do it, but that it's necessary. And kind of their purpose in doing so was to match the melt pool geometries. So you have a uniform melt pool, and to do that, you must kind of modulate power and slide it downwards as that difference from T-boiling to your part temperature decreases. So it wasn't necessarily that you had to do it, it's that for our purpose, to get these similar melt pools that we're going to control the process with, it's got to come down as that goes up.
Isn't it easier to just increase the power of the laser than like raise the whole temperature of the part? I'm just because of like energy conservation.
So you're asking instead of raising the build temperature of the part, just increase the laser power.
Yeah, because that has the same melt pool, right? So is it, I mean, I'm not sure, but I would think isn't it easier to like increase the temperature?
So the part temperature increases just as a byproduct of the process.
Right.
So you're not necessarily raising the temperature on purpose.
Okay.
It's a byproduct of you just putting a laser beam on that for hours at a time, and as that part gets bigger, you hold in more heat, and it's just gonna be hotter.
Okay.
So you're not actually adding energy into it on purpose. It's just
Part of the problem.
part of the process. So to deal with that, you have to slide it downwards to kind of keep the system
Right.
full size.
I had like one more question about the power density equation for the laser. Is it similar to the one we discussed on Tuesday? I don't, because the ADA seems to be, we had like an efficiency factor, right?
Yeah.
I don't know, does it relate?
So the absorptivity would be the same as the efficiency factor.
Or it's still a 2D equation?
So this was 2D. This is assuming equal variance in the x, y direction.
Yeah.
They're using different variable names here. They're using the radius of the beam,
Yeah.
which that's not really the radius of the beam per se, because the Gaussian has the radius.
Right.
It goes out to infinity each direction. Right? So this would just be basically the 1 sigma.
Oh, okay.
All right. They're adding this extra power distribution factor, but if you look at how this comes into play, you really, in the exponential is f over RP squared, and then the coefficient is f over RP squared. So not really two unique factors.
Right.
You can lump that into one variance, which is how it comes out. Then it becomes exactly the same.
Yeah. Thank you.
So to the, I guess, in your assessment, what was the main, if you go back to some of your earlier plots, you had this discussion. What is this next one? Right. So at the main comment here is the top, from the top, which is the top 2 rows here.
Right.
You would have noticed an appreciable difference in the, to your Melco camera. You would have noticed an appreciable difference in the, basically the shape of the Melco, but if you had somehow had the ability to get to the side of this, you could see this. So,
Right.
what is the, and you said the 2 things they tune is background temperature. Oh, sorry, in this case, sorry, it was the laser power and also essentially the variance of the laser, right?
Yep.
So so that's the process inputs that change this behavior.
Yep.
What was the physics behind why this changed? What's the main reason why you did this like that?
Right. So for the example on the left with the smaller beam radius, you've got essentially similar energy, the 450 watts and the 460 watts, concentrated in a much smaller location. So at that location, your temperature, which is this next plot here, your highest temperature right there in the middle, or right behind the laser, it gets a lot hotter. That power is so concentrated. It gets up to 2,900 degrees, and even the layers below that kind of feel that heat, and they get a lot hotter too. So essentially with the smaller radius, you're able to get that heat down into the sublayers quicker, and essentially heats them all up to create a larger melt pool. Whereas so I'll go back here, the other example, the 0.7 millimeter beam radius is kind of spread out more, so you don't get that big spike in heat temperature, and it just kind of affects the top layers almost. It doesn't quite penetrate deep down inside with that lower peak.
Getting into that, what do you notice about these factors that are different between plots? So if you look at just the temperatures, you wouldn't see a difference, but if I had the ability to look at the factors which are showing the velocity of molecules, what's the major difference?
Right, so it might be kind of hard to see up there, but kind of closer up here, the one on the left, the vectors are a lot larger. There's more velocity and fluid flow going on in the system, so more convection within that pool. One thing I've noticed too, in the depth view, you can kind of see some of the swirling happening that we've kind of talked about recently with that, what's the name? Starts with the G.
Has a G, Marangoni.
Yeah, Marangoni, thank you. Marangoni have effect in that pool, but with the concentrated laser, you definitely see a rise in the fluid flow vectors.
So you see a very, it's tough to see, like, it almost looks like little dots on the right. Because this is the velocity of the force above is varying by the convection. So on the left, it's taking what's material at the very center of the laser, which is the hottest, and it's via convection moving that to the edge, and also having it swirling down. And that's the major effect of light above. It's deepening the heat transfer from the center to the edges, and also it's rotating down. So it's a very effective thermal pathway to make the temperature of the bottom higher.
Yeah. You see the gradients, you see a whole new hot spot because it's like shades of gray. Aren't those like temperatures? So you have like a white spot.
Right.
Yeah. So that's a huge difference from the green.
Yes. No, there's no white spot.
Right.
I think, I don't know if they mentioned this explicitly, but in the Melpool camera, there's a difficulty in reading the very highest temperatures because you saturate it.
Right.
I don't know if they addressed that in that at all or not.
Not really. They kind of just mentioned that you could do this visually, looking at the melt pool, but they never really discussed how you would want to go about doing it.
So if you had just like a high-speed camera, you really can't tell the difference in temperature. You can see this is open, this is not open. So it's really good at a high-speed camera, maybe there's like a thermal camera, maybe. Other questions? This was a numerical study that, in terms of how numerical studies at the multiple level, it was not incredibly complex, but it had more complexity than a lot of things that we're going to look at in this class. But it shows you how numerical methods can really help our understanding here. Of course, it's not the focus of this class, it's more first principle relationships. This is a fairly simple numerical method. Just simple enough, it's nothing in terms of really interesting. All right, next round.
Here we go. Should be currently in use. Say it's currently in use, I should reject it. Out of it.
I just always just
It's alright.
I get that warning every time, and it's never been an issue. Okay. So the last thing that we talked about on Tuesday's class is we looked at the Biot number for kind of standard operating parameters for powder bed fusion. The question we were asking ourselves is, do we have to concern ourselves with the forced convection that happens in the system? Basically, heat transfer from this very top surface to then the air above, then it just gets exhausted out into some other internal system in the system. And we went through and we calculated the Biot number, which is how we look at this problem and try to understand, is this appreciable or not? And the main message here, after getting through all this, is that the Biot number was low. Right? And so we said that the convective heat transport into the chamber is not appreciable. And so after going through this little discussion, I decided to add this kind of build up in slides, just so we can have like a more codified way of looking at this. So if we looked at the very first thing we looked at was, does convection to the powder important? And we said this is unimportant, and then we'll continue to build upon all these here to say what's important, what's very important, what's important, what is unimportant. All right, we said that conduction to the unfused powder is unimportant. Going on to the Biot number, we said convection into the build chamber is largely considered to be unimportant when we model these physics. And the next question is, what about radiation? So this is basically radiation. If you have basically any two surfaces and there's a difference in the temperature, there will be radiative heat transport between these two surfaces here. So we can take a look at the literature, see what people have measured in terms of emissivity. If you look at the literature, this is a fairly large range. It's can be very dependent on quality of the particles, etc. But the emissivity range you'll see in the literature is somewhere between 0.27 and 0.35. And as a reminder, this is the equation for heat transfer via radiation. So this is conduction, which we've already covered quite a bit thus far, but radiation is we have the emissivity times the Stefan-Boltzmann constant, and then it's the difference between the temperatures to the fourth power here for radiative heat transfer. Okay. So as far as I know, there's not a certain non-dimensional number that quantifies the ratio of conductive heat transfer to radiative heat transfer, but we can definitely look at this in terms of a ratio, right? They have the same units. And so we can look at this problem here and say, example 5.2, we can do this kind of dummy example where we say we have a gradient in temperature, and so that this top surface is 1,000 Kelvin, which is getting kind of close to what Ryan was presenting for the paper. They looked at 500 Celsius, right? I believe the surface temperature. And then this bottom surface is 373, which is pretty common. This is 100 Celsius. Right? So we're definitely going to have conductive heat transfer because we have a temperature gradient in the solid metal. And then we're going to have radiative heat transfer because we have a surrounding chamber at 373, and then this top surface is at 1,000. Okay, so we can say, given these parameters for the system, determine whether or not radiative heat transfer at the top surface is appreciable. Is this going to be high or not? This temperature 1000 K is quite hot, actually. This would be kind of worst case scenario for radiative heat transfer. This would be your part getting extremely hot and staying hot for a long period of time. Is that heat loss mechanism appreciable or not? Okay. So working through this problem here, we've used 316L stainless steel a lot, so I'm not going to go through where these numbers are coming from because we've seen them in previous examples, but probably maybe almost memorized what the conductivity of 316L stainless steel is. 19.1 watts meters inverse Kelvin inverse, and so we can calculate kind of approximately, if we assume that this is a one-dimensional material, that the heat transfer rate from conductivity is going to be, here I'll write it out symbolically first, So it's negative T delta T over K, or over L, I mean. And so this would be negative 19.1. Watts meters inverse, Kelvin inverse. Difference in temperature, this would be 1,000 minus 373. And the distance at which it's traveled, is, we're saying that this block here is of height 0.05 meters. Or 50 millimeters tall, right? All right, so this gives us then heat flux via conductivity of 2.39 times 10 to the fifth watts per meter inverse, right? Oops. Not watts per meter inverse, watts meters inverse. Watts meters to the negative 2, I mean. All right. So this gives us just kind of a rough number. We're trying to say, all right, is this important or is it not, from a rough idea, right? So this is obviously not the exact. There are more things going on here than I'm showing here, but this would be simple 1D heat transfer. If we do this now for radiative heat transfer, okay, so this is our surface temperature to the fourth. This is the surrounding area to the fourth. And then we have epsilon, which we said in the previous slide that we're just going to use 0.35. We're going to use the worst case in terms of what would be the highest emissivity. And just to note, the Stefan-Boltzmann constant, sigma, is this. And this is a fundamental physical parameter. So we plug everything in here. Okay, so plug all these numbers in. If you look, we got watts per meter squared for conductive heat transport. If we look at the units here, we're going to get watts per meter squared as well, because this k to the negative 4 is going to cancel to this with this k to the 4, right? Those would cancel out. So we get the Q from radiation. So then we can look at the ratio of this, right? Trying to understand where is most of the heat going. All right, so ratio of radiative heat transport to conductive heat transport. Okay, is about 7%. Okay. And I would say this is a pretty much a worst case scenario here. So a very, very hot surface. Okay, so now it's not saying that the melt pool, which is a very small area, is really hot. That would actually be somewhat low for temperatures, but the entire top surface is very hot. So you have a large area for flux. So this would be kind of a worst case scenario, but the main thing here is if we do these kind of, yes?
So
So if we interpret this as saying 7% of the total thermal energy is radiation, or is this just like 7% of the total thermal energy dissipation is done by radiation, or?
So I think that's that maybe be reaching a little bit. We're basically just saying at this interface, 7% of the total. Well, it's not 7%. It's the ratio of the two is 7%, right? So if we look at heat transfer going in this direction and heat transfer going in this direction, this up arrow is 7% of the down arrow.
There's each conduction step 10 times larger.
Exactly.
Power.
Exactly. Yeah. That's the best, I think, interpretation. Now, I following up your question, it's not that there are other loss mechanisms that we haven't talked about. We get into evaporation and things of that matter in a little bit. But this is just saying that it's about 7% of conduction, which I haven't said it explicitly maybe yet, but I think it's becoming clear that's the dominant heat transfer mechanism, is conduction for the power. So we said before that the convection was less than 1%. We said that's not appreciable. 7% is getting to be somewhat appreciable in terms of something we may want to consider. So I would say this is the worst case scenario, but we say about 7% heat transfer through radiation. Okay, this is somewhat appreciable. Okay, just to kind of know the reason why I'm saying this is worst case scenario. So I'm saying that this is a part that's very hot. 1000 K, if you have your part held at 1000 K, that's quite hot to have it held there for a long period of time. And the reason why I'm saying that this is worst case is because the radiative heat transfer is T to the 4, and conductive heat transfer is T to the first power. Right? So as that part gets higher, then the radiative heat transfer becomes more and more important, much faster than conductive heat transfer. Okay. All right, so kind of looking at our chambers, I was really asleep when I wrote this. I would say this is somewhat important. Okay, there's a typo on my part. I would say it's unimportant. 7% is a decent amount. Right? Okay. So I'll make sure that's edited in the slides. Okay. Any questions about that kind of very loose kind of order of magnitude? Okay. All right. In terms of, we've defined some boundary conditions thus far. The order's not so great here, but we before we looked at these and we said that we have essentially a Newman boundary condition at the edges here. Okay, by saying that we have essentially no convective heat transfer into the environment, and that radiative heat transfer may not be too important, we can somewhat say that there should be a Newman boundary condition of this top surface as well. So there's no heat transfer into the environment above. The next question is, what do we do at this base? Right? And this is not really something we're putting equations here on, but it's worthwhile noting that each part is typically small compared to the build platform or build plate. Okay, and this is, I would say, typical. It's not that there aren't counterexamples to this. There are definitely counterexamples to this where they're building something so large that it starts to get to be on the order of the size of the build platform. But this is kind of just rough orders of magnitude, that these parts are usually just a fraction of the size of this build plate. So again, this build plate, this is on the order of a foot by a foot, and then somewhere around 3 inches thick. It's a really heavy piece of metal. and it's also connected to a larger machine. So this is bolted down to the machine below it, and so then even then, the actual thermal mass of the system is much larger than the parts itself. Okay. And so we think about this very, very large structure that doesn't change temperature very easily. Many researchers choose to consider the build plate to be an isothermal bath. And so they say that if the environment is brought up to a certain temperature, this bottom surface, this build plate, is held at that temperature, which is what we know as a Dirichlet boundary condition. Right? And then we say that this surface here, this bottom surface, we'll say is some sort of temperature T naught. Public temperature. So what this gives us is kind of this landscape in general for a simplified system. Basically Newman boundary conditions everywhere around the part, Dirichlet boundary condition at the very bottom of the part. Okay. Next question is convection in the melt pool appreciable? I think Ryan, with his presentation, just showed it is. But it's worthwhile going through and looking at some of the dimensionless numbers to try and describe this. So this is the Marangoni effect. So just this is the video that I played when we first talked about some of the basics of heat transfer. We talked about the Marangoni effect. As a reminder of what was going on here, this video that's on loop, they start hitting it with a laser that heats this surface, this hot spot. It's hotter in the middle than it is in the edges, so that creates a temperature gradient, which creates then a gradient in surface tension, which creates a shear stress, which then causes flow. And so now you get these vortices in the flow here, which is basically taking hot fluid in this region and pushing it towards the edge, and then recirculating it back. Okay, so this is convection, right? Mass transport of a fluid, which creates then a transport in heat. This is a numerical solution of Marangoni convection in laser powder bed fusion. This would be the start of the laser. What you can see is something you see very similar to what Ryan was showing earlier. You have radially extending velocity flow lines to the edge. When it gets to the edge, this is where we have solid metal. Then the flow lines have to bend down, and then it goes and recirculates in this direction. You can probably see it better on this side in terms of where molten metal is flowing. So going back to the dimensionless numbers that we looked at in, I think it was module 4, we can start to understand, all right, is the convection in the melt pool appreciable or is it not, right? And put some numbers on this. So we can pick up some of these numbers from the literature. So for instance, if you look at this survey article that we've been using a lot for 316L stainless steel, we can see that we have these values for viscosity, diffusivity, the solidus temperature of basically when this material is solid and when it's not. We can look at this change in the surface tension with a change in temperature. Note the negative sign here. And also we can start to look at worst case peak temperatures. All right, so Ryan is reporting, I think, a peak temperature of around 2600 K, even for the highest case, right? 29, okay, 2900 K. There are cases that you can find in the literature where they're bringing the materials all the way up to, say, around 5000 K, which is very, very hot. But this would give us, in terms of this Marangoni number, a worst case scenario to understand is this appreciable or not. All right. Melt pool lengths, these vary, but anywhere somewhere between 200 to 8500 or 850 microns for melt pool lengths. For this fundamental length here, L. So we can then plug this into the Marangoni number to see, and just a reminder, the Marangoni number is the ratio of surface tension driven or surface tension forces to viscous forces, right? So just kind of give you intuition on this. If we have a very strong surface tension force, there's a strong driver for material to flow. While alternatively, if there's a very strong viscosity in the fluid, that's going to be resistance to flow, right? So it's looking at the balance of these two forces and turning it into a ratio. That's the idea that we have the Marangoni number. Okay, so if we had an extreme like sludge, if this is molasses, which has a very high viscosity, it's not going to flow, right? Because the divisor is going to be a large number in that case. I don't know why you'd hit a molasses with a laser, but if you were to, right? So that's what the Marangoni number is looking at. And so we can start to put these numbers into this Marangoni number and look at problems like this. So this would be consider a circular pool of molten metal, 316L stainless steel. So just to kind of note, this, maybe I should say this is a half sphere. It's not a circle. Half spherical pool of molten metal. So we know this is not perfectly half spherical. It's some different shape, but let's just do this for the sake of an argument. The center of the melt pool is 5,000 K. This is the molten metal, so we know that the edge here has to be the transition between liquidus to solidus, right? So the edge, given the material properties, we know what this temperature is. It's 1733 Kelvin, right? At this very edge. Melt pool is 600 microns in diameter. Calculate the Marangoni number for this pool. All right, to understand these relationships. So Marangoni number, just repeating this. Okay, so from the previous slide, we had all these numbers given to us. Length, delta temperature, 5,000 K by 373 K. And then we have so the viscosity. And diffusivity. Okay. Throw this all in, we get 1.68 times 10 to the 4, which is a large number. Yes?
Would it be 5,000 K minus 373, or would it be 5,000 minus the solidus?
Thank you. That's an error. I have it right in my notes in front of me, and I just ignored looking at my notes. Thanks. 1733. Thank you. Yeah, background temperature doesn't matter in this problem. Okay, so this is a very large number, right? In terms of ratios, 10 to the 4, right? Okay, so what this tells us is that surface tension gradient-driven shear stress dominates. It doesn't just dominate by a little bit, it dominates by a large factor, viscosity driven shear stress. Okay, so this means material is going to flow in this melt pool. Right. And so I think this is obvious from all the literature we've been seeing, but this gives us kind of a sense of how strong that force is for the driving material. I'll take about a 5-minute break. We'll reconvene at 10:55, and then we'll get into, this is just whether or not the material flows or not, right? It's the balance of shear stresses. Now we just say, all right, is the heat transfer coefficient associated, or is the heat transfer associated with this flow appreciable or is it not appreciable? All right, we'll get into that after the break. Okay. All right, so now that we've established that there will be Marangoni convection, basically material is going to flow. It's going to flow quite readily. The viscosity is going to essentially do nothing to stop it, right? The surface tension driven shear stress is going to be dominant. The question is then, okay, we know that there's going to be some sort of velocity in the fluid. Is the heat transfer in the melt pool going to be primarily conductive or convective, right? We still have to answer this question in terms of a heat balance, right? And so this is the Peclet number, which is the ratio of convective to convective heat transfer to conductive heat transfer in fluids, right? So we could have, if I take the counterexample, we could have a material that the velocity is so small that the heat transfer is still driven by conduction within that fluid, right? So we have to understand whether or not if that's going to be the case or not. So the Peclet number is basically velocity times the characteristic length over diffusivity, and we know everything here except for the velocity, and we can again look at the literature and see what people report for velocities in the melt pool, and you see a bunch of the different numbers, but somewhere on the order of actually 5 meters per second, which is really, really fast if you think about what's going on here. Right? So in terms of how long it takes a molecule to go from the center of the melt pool to the edge of the melt pool is essentially no time at all. Right? If the melt pool is on the order of 100 microns and the those molecules are going 5 meters per second, that's really fast. The laser is going at most somewhere around 1.5 meters per second. So it's actually going faster than the laser's traveling. Okay. So melt pool velocity on the order of 5 meters per second from the literature. So we can do a similar problem as this. Consider a circular pool of molten 316L stainless steel. Fluid at the top of the surface has a radial velocity of 5 meters per second. So that would look like you have a molecule starts in the center, it's going to go to the edge in some direction, right? Depending on where it's at. And the melt pool is 600 microns in diameter. Determine whether heat transfer is dominated by conduction or convection in this melt pool. So Peclet number. All right. We have diffusivity from previous work. We're filling this in. We have 5 meters per second velocity. All right. Characteristic length. It's only going half of the melt pool distance, actually, right? Starting in the center, so this is going to be 300 times 10 to the negative 6 meters. Diffusivity. This. All right, gives us a ratio of 22.5, or 225.6. Okay, so what this is telling us the ratio of convective heat transfer to conductive heat transfer in the melt pool is 225. So it's almost purely convective heat transfer in the melt pool. All right, conduction makes essentially no difference at all in the melt pool itself. So going back to our chart here, convection in the melt pool is important. I'm omitting calling this very important because the melt pool is actually a pretty small space. So if you look at heat transfer through the entire part, once you get outside the melt pool, there's obviously no convection, right? Because it's a solid metal, right? But this is important. It's a lot of people choose to model this. Okay, but this is going to be an important factor. We're going to start by a little bit omitting this to make our life easy at first, because convection is very difficult to model. But this is an important factor. And you see a lot of the computational methods that for powder bed fusion and E-beam, they include convection in it because it is such an important factor. Okay. Next one I want to talk about is evaporation or boiling in metal. And so this is something that is a little bit difficult to pin down in terms of actual numbers, but this is something that definitely happens and is definitely important. So we saw a few things. Maybe I'll go back a little bit to some of those videos we looked at. Even maybe these stills would be important to look at. So we saw a few features here. One is this divot that happens at the laser spot. And so nothing that we've talked about thus far really explains why this divot exists. Right? So we'll talk about that now. We also talked about this spatter that flies off. And these still images don't show it very well. This video here, you'll see this is a computational study. You'll see spatter that flies off this thing. There you go, one of those, spatter, right? This video shows it enough, right? So you have this divot here, or this depression. You have spatter flying off. Okay, the question is, why does this happen? Right. Whoops. Yeah, there's a video I want to show. All right, so why does this happen? We also saw this migration of particles into the melt pool, and some of this almost looks like the Jedi Force is happening, right? So you would expect that powder could be recruited in the melt pool via capillary forces if it were to touch it, but some of these seem like they're coming from pretty far away, and almost as like there's some sort of traction force bringing powder into this melt pool. We want to know, why is this happening, right? It seems kind of not physical. Okay, so not too many equations surrounding this one, but just kind of give some general physics of why this is happening. It has to do with evaporation. Okay, so if you heat up anything to this gaseous temperature, you're going to have evaporation, right? It's going to turn, in this case, it's turning from solid to liquid to gas, right? All right. So, and then if you look at a lot of literature, you get statements in terms of the fluid necessarily expands while transforming from liquid to gas, right? This is what you've probably seen in freshman level physics, sophomore level physics. If you've taken heat transfer or thermodynamics classes, you've seen this via the ideal gas law, right? But the fluid expands, right? So, fluid is expanding, and then when it changes from a gas, it rapidly expands. Okay, so what you get in this expansion is that you get a high pressure region right in here. Right. So this is, just to orient you, this is solid metal. This area is liquid metal. You can see Marangoni convection in the liquid metal. And you're going to get a gaseous region from the evaporation of the metal here. Causes what's called a recoil force, analogous to what is created by the gas emitted by a rocket engine. This is just quotes from this paper. So this recoil pressure is basically the mass evaporation rate squared here, and then the ratios of densities. So basically, if you are heating this up to be very, very hot, you're going to have a very high mass evaporation rate because you have higher temperature distributed over a larger area, therefore more mass being evaporated more quickly, and then this pressure is going to increase. Okay, so you have very high power laser, you get a deeper divot that's forming. We saw that in the X-ray images as well. We got a very large plunge of this divot into the part via a higher power laser. All right, so we get a bubble here with very, very high pressure that pushes down the melt pool into the part, and also is going to create on the top side a velocity stream going up in this direction. its recoil pressure. So think of it as a really high pressure bubble pushing out in all directions, and also is creating gas flow at the top at this surface here. And so that explains the divot and why that happens, right? The other one is, why are these particles seeming to come from pretty far away and being now entrained into the melt pool? And this has to do with something called the Bernoulli effect. So those who've taken fluid mechanics, you probably remember the Bernoulli effect, but the main idea here is that if you have a flow field and you have part of that flow is at higher velocity than another part, then the pressure in the high velocity area is going to be lower than the pressure in the low velocity area. And so this is this you can pull from Wikipedia, pretty simple, but you have this flow, you have wider diameter channel here, smaller diameter, that means the velocity here has to be higher than here. So you get this pressure differential, where this is a delta P across these two different ports here. So this is going to be P high, and this would be P low, and you can see this from a differential manometer here. Okay, so we have, what we have here is we have very high pressure bubble here that then creates a flow stream because you have high pressure to low pressure, so we get now air, or I guess the gas in here, which is now a mixture of basically evaporated metal and argon gas that's in the chamber, creating a very, very high velocity of flow right here, which creates a low pressure area right above this. And so higher pressure, lower pressure, you actually get powder to be basically swept up in that fluid flow stream and be thrown into the melt pool. Is the main explanation of what's going on there. Keep in mind, this creates what's called a denuded zone. So this actually leaves a vacancy of powder in the regions just adjacent to the melt pool. Actually, because you have powder being taken from where it normally was or where it was placed, now thrown into the melt pool. Okay. Any questions about those kind of general physics there? Okay, so this is important. It is a heat transfer mechanism. A lot of works choose to ignore this. The really highly computationally complex work out of Lawrence Livermore National Lab, they include it in some of their simulations, but the vast majority of simulation packages, physics packages, ignore this effect. There's actually maybe just a handful of papers that look at this because it's pretty complex. I guess would be the best explanation for it. But this is kind of the landscape here in terms of what's very important, what's unimportant, etc. We're going to start getting into some very, very simple temperature relationships and understanding here, and we're going to basically make these statements. We're going to, at the very first part, consider just basically just, maybe I'll erase that. We're basically just going to consider conduction through the part at the very first pass. And then we'll build up the complexity from there. Okay. Sound good? Okay. Okay, so if we make all these basically simplifying assumptions here, and we'll build from here, what we're really talking about is, we're not talking about the actual process of powder bed fusion, which is converting powdered metal into metal. We're really talking about a very simplified example where we have just a solid piece of metal and we're running a laser over top of it, and we're trying to understand what is the temperature profile. So it's not powder bed fusion actually, it's somewhat close, and we're trying to understand temperature relationships and how that actually corresponds with what you would see if you were to actually try and melt powdered metal on top of a metal surface. Okay. So assumptions is basically we're just running a laser across the top surface of a large piece of metal at a constant velocity. No heat transfer from top surface to environment. So that means no convection, no radiation, no evaporation. This is the Newman boundary condition at this surface here. The piece of metal is we'll start off with this very simple assumption that the piece of metal is thick. All right, so that means that H, being the thickness here, is much, much greater than the melt pool depth. That's what we're going to assume to begin with. That's the first thing we're going to remove from an assumption a little bit. The density, specific heat, conductivity, these are all constants. And we're saying no evaporation, no Marangoni convection. We're trying to simplify this as much as possible. Also, this is, I forgot to mention, constant velocity laser profile. Okay. So this is essentially the Rosenthal paper, just to begin with, to give us baseline. When we presented things from the Rosenthal paper before, we really didn't apply material properties to that, and so now we'll start to apply material properties to this. I wanted to go through this, though, in a little bit different fashion using non-dimensional numbers. I think that's going to be the best way to try to compare the different factors that influence temperature profiles in powder bed fusion. And so I won't be able to finish this example today because we only have 5 minutes left, but I'll start with the non-dimensionalization of this PDE. So if we look at this example, we're going to look at 150 watt laser. This is fairly low power, running at, we'll look at a few different velocities, but these are all to be fairly low velocities. Well, I guess one will be quite fast. The other ones are pretty slow. And the block of metal is an environment regulated to be 373 Kelvin, which is 100 Celsius, right? Plot the non-dimensional temperature of the block using a moving coordinate frame. Zeta or xi is equal to, I guess it's like, that's zeta, yeah. Zeta is equal to x minus vt. All right, so what we're looking at here, with the assumptions we're given, we're essentially looking at the diffusion equation. And this is coming directly from our modules on heat transfer, right? The diffusion equation for the unit cell. This Q, we're assuming very simple characteristics for the laser source. It's not distributed at all. That we have Q is equal to the power, and then the Dirac delta function. And then, of course, we have a domain. And we're saying a large block of material. So a large H as well. And so we can assume, and then we'll start to weaken this assumption a little bit. We'll see what the difference is. But we can now assume that we have a domain stretching from negative infinity to infinity in the x direction, negative infinity to infinity in the y direction, and negative infinity to 0 in the z direction. Newman boundary condition at the very top surface. And if you go back to our discussions from heat transfer, we can also rewrite this in a different fashion. We can say that the Laplacian of the temperature at 0 dot product with a normal vector, so this would be of that surface, is equal to 0. So this normal vector would be 0i plus 0j plus 1k. All right, so a vector going just due north, along the z direction. Okay. So going back to the Rosenthal paper, the first thing we did is we did a change of coordinates, right? We wanted to turn this spatial temporal PDE purely into a spatial PDE, and so I'm not going to go through that because we've already gone through that. But we got this new PDE once we make this change in coordinates, with this change in coordinates, zeta is equal to x minus bt. And then basically the boundary conditions, etc., domain follows pretty simply here. So as we were doing when we look at the ideas of non-dimensionalization, we're going to use a non-dimensional temperature here. All right, so we're going to say our non-dimensional temperature theta, and we are going to normalize this 1 by the background temperature. So this is T naught. And we don't really know what the maximum temperature that'll be felt here is, but a good normalization factor is the liquidus temperature of this material. All right, so we know that if this theta is equal to 1, that means that's the boundary between melting and not melting. That's a really good point to try and understand if we want to understand what the melt pool is. So our normalization, our denominators then become then TL minus T naught. Okay. Just for your notes, this is liquidus temperature. Okay. All right, so alternatively we can write T is equal to TL minus T naught theta plus T naught, right? Just rearranging that. And so what this, sorry, I think people are still writing out. Hold on a second. All right, so then the very last thing I'll do before we adjourn for today, the weekend, is we just then plug this into the PD that we already had. I'll do this in long form just so you can see what's going on. All right, and with that amount of time, I'll show you how this becomes, how the PD changes in terms of being non-dimensional. I'll show you where I made a mistake on the non-dimensionalization in Module 4 and what the correction for that is. But then we'll get back to this on Tuesday then. Any questions on this? All right. Have a nice weekend, everyone.